So here we are finishing up our section on continuity. We have some properties of continuous functions. No big surprises here with these, in case you were looking for surprises. Really, it just tells us that if we have a couple functions, f and g, they are continuous at a value. And if we have a constant called c, which is very common for a constant, that if you take your constant and you multiply it by f of x, if you multiply two functions together, those two functions, or if you add or subtract them from each other, they are still continuous at x equals a. And that's, of course, because of what we have up here. Not surprisingly, we also have some continuity if you divide the two functions, but we can never forget that we can't have that denominator being 0. So if g of a is equal to 0, we have a problem. So we have continuity as long as g of a is not equal to 0. Now, in terms of composition, it's really just the fact that, like, say we have a limit as x approaches a of g of x, say it equals L. Say f of x is continuous at x equals L. Then we have all this notation here, which basically just says that, kind of the big one I think, is that you can bring the limit into, because f is continuous at this value, this limit value for g of x. So you can bring this limit in and then evaluate there. And then that can be helpful sometimes. So that's a lot of what the composition and continuity talks about. I say it in a few different ways, but it's all very similar notation. So the last one here just says, hey, you got an elementary function. It's going to be continuous where it is defined. If you are thinking, what exactly is an elementary function? I'll give you the precise definition of that. It is, the most basic functions that we have in calculus. And typically that would be anything algebraic, your lines, all the polynomials, quadratics, all that stuff, as well as exponential, logarithmic, trigonometric, and hyperbolic functions. So those functions are all continuous where they are defined. So let's take a look at using continuity to find a limit. The big thing here is to kind of consider that if you have an outer function and an inner function here, this thing we're taking a limit of, take yourself back to our composition, think about that. Inner function, well, it's the thing in parentheses. Outer function is going to be sine x, that's the one on the outside here. Okay, and then we just want to use the idea of continuity here. So to find this limit, as x approaches pi of sine of x plus sine x, what some of these properties above are saying is, because x plus sine x, if I come over here to these two functions, both of these functions are continuous for all real numbers, actually, and definitely they are continuous at pi. Because when you think about it, even though sine of pi is 0, that doesn't matter. What matters is sine x is continuous. And since x is continuous, and sine of x is continuous, adding them together, you still have that continuity on all real numbers. So what it tells us is that we can bring in this limit. So we can have sine of the limit as x approaches pi of x plus sine x. There you go. And now that we can look at it this way, now we can say, okay, since that's continuous, now we can plug in our pi. And we get pi plus sine of pi, well, that's pi plus 0, and sine of pi is just 0. So using continuity, we get the answer of 0. So now I'm going to switch it up here at the end for this last little bit. We're going to talk about the intermediate value theorem. That is also at times called the IVT. So let's say we have a function on a closed interval a to b. So that's what we're seeing here. So we're on this interval from a to b. Okay. Now, we have any number n between f of a and f of b. So n is a y value, as you can see. It's a y value. Anywhere between f of a and f of b. Switch. So what it's telling us is, since this function is continuous from a to b, if you choose any number n, but y value, there will be an x value. There will be an x value such that when you plug in the value, you're going to get that n, because it's continuous. So as long as there is an n between f of a and f of b, any n between those two, you're going to be able to find essentially the x that goes along with that. So big things here for the IVT, you have to have a function that is continuous. So if you were to have something, so think about something that's not continuous, picture a not continuous function. If you were just like, okay, it's going to go here, and then it's going to go like down to here, and then it's going to be up here, and then it's going to go like this. Okay. Right here, because this is discontinuous, it has a discontinuity in it, IVT doesn't work. Okay, you can't, the IVT is not something you can use. You have to be continuous on the interval. Now, notice that the interval has to be closed. So you also don't have that guarantee if you had, for example, here and, you know, whatever you want to do, and then you have this hole. So that's going to be a problem. The interval has to be closed. If you have open endings, the IVT does not give you this guarantee. So you want the closed interval. Now, the big applications of that are if you have a function that is continuous on an interval and your y values, so the function is continuous from a to b, and your y values have opposite signs. So one is positive and one is negative. Then your function must have a root or a zero. There's a couple different ways you can say that. In that interval where when you find the y value, it's zero because, I mean, it has a root. So it's a pretty like straightforward thing that comes from the IVT. So as an example, you have a function that's continuous on an interval that is closed. So if I had this, and we want to remember that f of a and f of b have to have opposite signs. So I might be like this as an example. So of course, because it's continuous on this interval, I have to be able to draw something and not have to like pick up my pen. So here's an example of a function that follows this. Again, big thing here, f of a, f of b have opposite signs. So I've got to be starting in the negative and going to positive, or starting at positive and going to negative. So what this is telling us is that there has to be a root, meaning that there has to be some value c for which, if this function is f of x, well, there has to be a value for which f of c equals 0. So there's some c in that time, like that interval. And the way that we use this typically is we show that some equation has a solution. So we want to remember when we have a function like that this can be seen as, here's a function, x cubed, I mean, that's an equation, but here's a function. And we just want to know, when is that equal to 0? And if it's equal to 0, that means it has a place where it's crossing the x-axis, meaning it's an x-intercept. And so the IVT basically guarantees that if certain things are satisfied. So we might say, well, I don't know, does this have a root? And that's the same as saying a solution to this equation here on this interval, 0 to 1. So we don't know. So what we do to use the IVT is we check. Okay, so remember the IVT says we have to have a continuous function. So that's a x cubed minus 3x squared plus 1. That's a polynomial. So it's continuous. It's continuous on all real numbers. So it's definitely continuous on that interval. And of course, it is continuous. Even more importantly, it's continuous on the closed interval, which is required for the IVT. Continuous on the closed interval. And that's what we need because it's polynomial. So we do f of 0. So I have 0 cubed minus 3 times 0 squared plus 1. And that gives me 1. And then I check f of 1, because this is, I'm taking that from over here. I check 1, I get 1 cubed minus 3 times 1 squared plus 1. If we evaluate that, we get 1 minus 3, which is negative 2, plus 1, which is negative 1. So the key thing to see here with this example is that when we're at f of 0, we're actually at 1. And then at f of 1, we're at negative 1. So somewhere in between there, what the IVT says is somewhere in between there, it has to cross the x-axis. How does it go from a y value of 1 to a y value of negative 1 without crossing the x-axis? The IVT says it has to. It has to do that. So again, that's because this is greater than and this is less than 0, and so it satisfies the requirements for the IVT. So now we can say, thus, very mathematical, thus, by the IVT, it's okay to say IVT because intermediate value theorem is long, IVT, there exists a C, and then I'm going to use set notation here, C in from 0 to 1. So this just means is an element of, that's just like, you know, more mathy notation there, with f of C equaling 0. So again, a very common use of the IVT. And that is section 1.8.